So today we're talking about translations. Last week we talked about reflections, and we're going to incorporate that a little bit. We're also going to talk this week about rotations. But a translation is a transformation in a plane that maps all points of a pre-image the same distance and in the same direction. It is also called a slide. Okay, so it takes and moves something the same distance in the same direction. The translation of a triangle by x units along the x-axis and by y units along the y-axis can be written like this. And so they use a capital T, and then you see how it's got little, they're not parentheses, but they're little sideways V's. Okay, that's called vector notation. And so you have an x and a y, and then it puts the triangle ABC and then equals triangle A prime B prime C prime. So basically what this is saying is a translation of triangle ABC through this vector, which maps onto A prime B prime C prime. Now, a vector is a directed distance. Okay, like when a pilot is going to fly from here to Oklahoma City, he has to file a flight plan with the FAA. Okay, basically he says, I'm going to go from here to there. I'm going to go this distance in this direction. Okay, it's kind of like a ray, but a ray goes on indefinitely. A vector has a starting point and a stopping point, and it has a specific direction. Okay, and so what's happening is it's taking here, this right here, ABC is my pre-image, and it's taking and it's translating each point a specific distance and direction. And it's translating this point B onto B prime and C onto C prime. Okay? And notice that the path that each one of them takes is parallel to each other, right? If it wasn't, this new image would be distorted from the pre-image. Okay? And so you have to go the same distance in the same direction. And see, and I've noticed, I've denoted here that these paths are parallel to each other. And the distance that they travel is the same also. Because if the distance wasn't the same and the direction wasn't the same, then you wouldn't get the same shape in the end. Okay? So does that mean through a translation, do you get rigid motion? Yes, because the size and the shape does not change. Okay? And they have the same, and they also have the same orientation. Whereas in a reflection, you could look at the points and you can see that it was reflected. But you can see here, they don't change. They're in the same orientation. Okay. When you're trying to figure out what translation has happened, it's always important to look at the letters and where the primes are. Okay, and that will kind of help you know if it's a reflection or a translation or a rotation. But a translation is rigid motion. The length and the angle measure are preserved. Okay, so what is the graph of a translation of triangle EFG through the vector 7, negative 4 that gives us E prime, F prime, G prime? Now I'm going to show you two different ways that this can be done. Okay, you can take and just graph it. Okay, and so here is my pre-image, and this tells me that I'm going to go 7 units to the right and 4 units down. Okay, positive is right, negative is left for your x, just like when you're plotting a point. Positive is up and negative is down for your y. Okay, so I'm going to take each point and I'm going to go 7 units to the right and 4 units down. So I'm going to take my E and go 1, 2, 3, 4, 5, 6, 7, down 1, 2, 3, 4. Okay, and that's going to give me E prime. And then I'm going to do the same thing with F. 1, 2, 3, 4, 5, 6, 7, down 1, 2, 3, 4. There's F prime. And G prime, 1, 2, 3, 4, 5, 6, 7, down 1, 2, 3, 4. Okay, and there is G prime. Alright, so I've translated my triangle to the right 7 units and 4 units down. Okay, now you can also do it with your vertices. Okay, it says what are the vertices of E prime, F prime, G prime after each translation? And obviously we can just look at it. But another thing that can be done is you can take your original coordinates. Okay, so let's look at E, F, and G here. Okay, E is located at negative 5, 4. F is located at negative 1, 5, and G is located at negative 2, negative 1. Okay? Now, let's say we didn't want to graph it, right? We could apply this vector to each one of these points. And so if this right here is positive, that means I would add 6 to the x, and then this is negative, I would subtract 7 from the y. And then I would do that with each one, and then I wouldn't have to graph it, okay? So that means that E prime then would be 1, negative 3, oh, it's a different one. I was like, wait a minute. Okay. Hold on. Let's go back up here and look at this one. Hold on. Oops. I did this differently last hour. Okay, I'm going to put this up here. So E is at negative 5, 4. F is at negative 1, 5. And G is at negative 2, negative 1. Okay, I used this vector and I didn't realize they were different vectors. Okay, so again, if we added 7 and subtracted 4 to each one, okay, we would get what, 2, 0. Here we would get 6, 1. And here we would get 5, negative 5. Okay, so 2, 0, 6, 1, and 5, negative 5. Okay, so you could do this in lieu of graphing. Okay, it may ask you to do it one way, it may ask you to do it the other way. You need to be able to do both ways. Okay, okay, so here's a different one using the same pre-image, but they gave us a different vector. Okay, so here we're going to add 6 and subtract 7, add 6 and subtract 7, add 6 and subtract 7. Okay, and so we're going to get a new E prime, F prime, and G prime without graphing. Okay, all right, so what would my E prime be? 1, negative 3. And what would my F prime be? 5, negative 2. And my G prime would be 4, negative 8. Okay, so we could do a transformation without even having to graph it. Okay, another way that they might denote it, I have it written on the sideboard over here, is they might say, give me a transformation of like this, and I'll use these coordinates, and it might say x plus 6, y minus 7. Okay, so basically you're adding 6 to whatever your x is and subtracting 7 from whatever your y is. So they might give it to you in that notation as well. Okay, honestly, I'll be honest with you, my book that I had for 20 years never used that notation. We always used something a little bit different. So, I mean, they had vector notation, but that's just not how they wrote it. So, but anyway, times change, things change. Okay, you might be asked to go backwards, okay? And if you were asked to go backwards, what's a translation rule that maps STUV onto S prime, T prime, U prime, V prime? So what you have to do is go and see what did they do to get from S to S prime. And you have to do the same thing from T to T prime, U to U prime, and V to V prime. So you go up here to your pre-image, and to get to S prime, do I go left or right? Left 1 and down 4. Okay, so left is positive or negative? Negative. Okay, so that's negative 1, and down is negative 4. So if I wrote it in the right notation, I would do a translation, and then I would put a little vector down here, negative 1, negative 4, okay, and then it is STUV, and it maps onto S prime, T prime, U prime, V prime. So that's looking at what happened and you giving me the correct transformation. Okay, here's another one. What is the translation rule that maps P, which is at negative 3, 1, to its image P prime? So if I'm going to go from P to P prime, what am I going to have to do? Go to the right, 1, 2, 3, 4, 5, and go up 2, right? Those are both positive, yes? Okay, so it's a translation, and then you put the little vector notation, positive 5, positive 2, and then the point is P, and it maps onto P prime. Okay. Be careful when you're doing this. Don't get it mixed up with slope. Okay. When plotting a point and doing a translation, you do left, right, then up, down. Slope's different, right? Rise over run. So don't make that mistake. We did it last hour. Oh, I messed up. But anyway, be careful with that. Don't get those two processes mixed up. Okay. Now we want to talk about what happens when you do more than one transformation at a time. Okay. This is called a composition of rigid motions. It's a transformation with two or more rigid motions in which the second rigid motion is performed on the image of the first rigid motion. Okay, so it looks like this, okay, and see how it's got a reflection over line L, and then it's a translation through the vector negative 2, 5, okay, and we're moving triangle ABC. This little circle denotes a composition of rigid motions. A small open circle indicates a composition of rigid motions. Now, the way they write it is a little weird because they write it like this, but when you go to do it, you have to do the second thing first, okay? So you have to do this first, and then you have to do this second, okay? And so this is what you do to the original pre-image, okay? You do whatever it tells you to do, right? And then you get an image, but that becomes your new pre-image for the second thing that you do, okay? So you use what you've changed to do the second one. For example, here is a reflection and a translation for AB, okay? All right, so we come over here to AB, and we're going to do this first, all right? So that means that we're going to take this, and we're going to go left or right, right 3 and down 1, so that would be B prime. Okay, and you're going to do the same thing here to the right 3 and down 1. That's going to be A prime. Okay, then we're going to go here and we're going to reflect over the x-axis. So if I'm up 2 above the x, I got to come down 2, right? That's B double prime. And A is 2 units below, so when you reflect, it becomes 2 units above. Okay, and so that is your final image. Now, you can also do it with just the coordinates, okay? A is located at negative 2, negative 1, and B is located at 1, 3. Okay? All right, so let's take A first. And the first thing that we did was translate, correct? So that means that we're going to add 3 minus 1, okay? So that means my coordinates would be 1, negative 2. Okay? For my B, those coordinates, if I added 3 and subtracted 1, would be 4, 2. Okay, so let's check that. 1, negative 2, and 4, positive 2, right? Okay, then to get to the double primes, we have to reflect over the x-axis. What's the rule for reflecting over the x-axis? No, they don't switch places. The y changes signs, okay? It is not necessarily negative because it's already negative, right? It has to change signs. It's like multiplying by negative 1. So this becomes 1, 2, right? And this becomes what? 4, negative 2, right? So we check it. 1, 2, there's my A double prime, and my B double prime is at 4, negative 2. Okay? All right. So we graphed it, but we also used our rules. Okay? So just depending upon the information they give you is probably going to be the easiest thing to do. Okay? You need to know how to do both. Okay. In learning a new dance, Kyle moves from position A to position B to position C. What single transformation describes Kyle's move from position A to position C? Okay, so from A to B, okay, from A to B, he went 2 to the right and up 2, right? Okay, so 2 to the right, which is positive, and up 2, which is positive. Then he went from B to C, right? And from B to C, what did he do? You go down or to the right first? You got to go to the right one and down one, right? So what would that vector be? 1, -1, right? Now it says, what transformation would describe going directly from A to C? Okay, so from A to C, what would it be? To the right 3 and up 1, right? Okay, so do you notice anything? Right. When you have two translations, okay, you can actually combine it into one and just do it one time. But that only works with two translations, okay? So see how if I had added those two together, I would have gotten 3. And if I had added those two together, I would have gotten a -1, right? Okay? So, with that in mind, and remember, it only works when you got two translations, okay? What is the composition of the transformations written as one transformation? What would this be? You have a translation of 3, -2 and of 1, -1. 2, -3? What about 4, -3? 4, -3. Okay. Now, when you're writing this, it's important to use the right notation, okay? Don't use parentheses because that's not what it is, okay? It's little sideways V's. It's a vector notation. And I say this because, like on the test, some of us didn't use the right symbols on our test, okay? Like the answer was supposed to be L parallel to M, and I had some people put that. What does that mean? Congruent. Can lines be congruent? No, they're indefinite, right? Okay. And so it's important in math to know what the right symbols are. And this is the vector symbol, okay, which indicates your translation, okay? Okay. All right. Let's look at what happens when you have two reflections over a pair of parallel lines, okay? How is the composition of reflections across parallel lines related to a translation? Okay, so step 1, we're going to reflect triangle ABC across the y-axis, okay? So here is a reflection across the y-axis. Look at ABC and then see how it reflects and comes over here. We've got A prime, B prime, C prime, right? Okay, reflected. You see that? Okay. Then we want to reflect over line M, okay? This right here is line M, okay? So they're going to take this new image, right, which now becomes my pre-image, and I'm going to reflect it back to the left over line x equals 4, right? Okay. All right. So what happened? What ends up happening in the end? It's just a translation. If you have two parallel lines, you reflect over one and reflect over the other, you actually end up with a translation. Do you see that? Look at the letters. See, A, B, C, the order in which they are. Look at this right here. The arrow, I reflected, and then I reflected again, but what is it? A translation. Okay? All right. Now, let's see if we can figure out what the translation is. Okay? Notice the difference between the parallel lines. How many units is that? 4 units, right? There's 4 units between the parallel lines, okay? Now, look at B to B prime. There's 1, 2, 3, 4, 5, whoops, 1, 2, 3, 4, 5, 6, 7, 8 units, right? 1, 2, 3, 4, 5, 6, 7, 8 units. 1, 2, 3, 4, 5, 6, 7, 8 units. So when you reflect over a pair of lines that's 4 units apart, what's your translation going to be? double that, right? Okay, so you're going to move each point 8 units that direction, okay, that you're reflecting over, okay? And so that's what it says right here. Notice that the distance between the corresponding points on the y-axis and line M is 4 units, okay? So from B to B double prime to A to A double prime and C to C double prime is 8 units, okay? So if triangle ABC is translated 8 units to the right, its image is also triangle. Okay, that's just telling you that. Okay, so here it is in symbols. If we have this composition of reflection, reflect over the y-axis, then reflect over the line M, we actually get a translation of 8, 0, okay, because we're moving 8 units to the right, okay? All right, here's another one. Suppose N is the line with the equation y equals 1. What kind of line is y equals 1? Horizontal through 1, right? Okay, so we're going to reflect over this line, right? And so you've got your vertices. I've already graphed it. So suppose N is the line with the equation y equals 1. Given DEF with the vertices, what translation image is equivalent to a reflection over the x-axis and over the line N? Here's the x-axis, right? So what are we going to do first? We're going to reflect over the x, correct? And then we're going to reflect over the line N, correct? So we're going to take and do this, and then back up here, correct? Okay. What's the translation equivalent to? Do what? 0. Well, the distance between the parallel lines is 1, right? But when you change it to a translation, you double it, right? So it would be a translation of 0, 2, correct? Okay, a translation of 0, 2. And we're moving up, so it's a positive 2. Okay? Because we flip down, but then we flip back up, so everything shifted upwards. Okay? All right, now, answer this for me. Is there anything in the whole wide world that you might use this for? Or am I just teaching you stuff? Am I just teaching you fluff? You think anything that you might ever use this for? Not one single thing.
Designing storage.
Designing what?
Store.
A store?
Yeah, for where the shelves are and stuff.
Okay, possibly, you know. Building a house, maybe, yeah. Yeah, if you wanted to move, to shift something, like from one location to the other, okay. Okay, yes. Blueprints, okay, good, good. Has anybody ever seen a cartoon? They use it all the time. That is how they do it. Okay, that's exactly how they do it. Any Pixar, anything that you've ever seen animation, this is how they do it. I taught computer programming my very first year, okay, and the most exciting thing that we did the whole time was make something move. Anybody in here in video gaming or video design? Nobody? Okay. We would make something shift, and we had to use translations. I remember when I was a kid, you know who Woody Woodpecker is? Okay. There was like one of those game books. You know how you had all the different activities in it? And I remember there was always a picture of Woody Woodpecker, and they wanted you to like change it a few times, right? So you took the original picture, and then they told you change it, change it, change it, change it. And then if you went and flipped it, what happened? It starts moving, doesn't it? Okay? That's what this is. All right? So in order to make that happen on the big screen, they have to use all this math. Okay? I have a video that I'll show you probably one day this week that incorporates some other things as well. All right, so we talked about what a translation was, also called a slide, right? And that takes and moves something left, right, up, down. Okay, here's the notation for it, the little vector symbol. Okay, make sure you understand that. We talked about going backwards with that. Okay, then we said that if you do a composition of transformations, what do you do first? The second thing and then the first thing, right? Okay, and the composition is a little open circle, okay? And then what happens when you do two translations in a row? You can put them together, right, for one translation. What if you do two reflections over a pair of parallel lines? Then it's a translation. And how far do you translate? Double the distance between the parallel lines, right? Okay? And I think that was it.